Hey everybody, this is Mr. Ainsworth, and we're going to get into the third section here in Chapter 5 in graph theory and talk about some graphing concepts and some terminology to allow you to understand Euler's theorems later on in the chapter here. So let's get right into it. Let's talk about what are called adjacent vertices here. All right. So let me define it first, and then we'll go through a bunch of examples here to exemplify it. All right. So adjacent vertices are two vertices, or you can say nodes if you want to say nodes, all right, either one, joined or connected by, all right, an edge. Keyword is an edge here. Okay, that's all there is to it. So if two vertices are joined by an edge, they're adjacent. If not, they're non-adjacent, all right? We also say that a loop is adjacent to itself, so remember that. It's a little side point right there. All right, so let's go through by example and try to understand it. So if A is, the first question is A adjacent to B? Well, let me see. Here's A, all right, and here's B. They're connected by AB, which is an edge. Therefore, they're adjacent. Okay, so we're going to say yes, all right, edge AB exists. That's the justification. Yes, it is. If the edge exists, if it's there, then A is connected to B, or we say is adjacent to B. Okay. If this edge AB was not there, then I would say they're non-adjacent. Okay. So since it exists, then I would say uh, that A is adjacent to B. The next question is E adjacent to itself. Well, I notice over here there's a loop. All right. And up here it says loops are adjacent to themselves. Okay, so E, since it's a loop, is adjacent to itself. So I'm going to say yes again. EE, which is a loop, all right, exists. It's on the graph. All right, there's a loop right there. So since there's a loop at E, not just an edge, but a loop, E is adjacent to itself. All right, is D adjacent to A? And I would say no. There's a path to get from D to A or from A to D, but there's no edge like this one right here, if I connected one, at D to A or A to D. And because of that, because that doesn't exist, we're going to say no again. So no, the edge AD does not exist. Okay, is C adjacent to itself? Here's C up here. There I don't see a loop up there. So I'm going to say no again. So no loop, which we're going to call CC, loop CC does not exist. Only loops are adjacent to themselves. So if you don't see a loop, that's not true. Okay. Now, if you can have adjacent vertices, you got to have adjacent edges. All right. So I would say, just give me an example, that AD here is adjacent to AC. Or I could say that AB here is adjacent to AD. Or I can say that CB here is adjacent to DB. Or I can say those, make those statements, okay, because those are adjacent. But I cannot say that AB is adjacent to DE here. And I cannot say that AB is adjacent to CE because there's a big difference there. So what is it? What makes AB adjacent to BC and not CE? Or AB adjacent to CB and not DE? What makes that happen? Well, if you look at these two edges here, they have something in common, and that point in common is called a vertex. All right, so that's how you define adjacent edges. Two edges are adjacent if they share a common vertex. So adjacent edges are two edges, all right, that share a common vertex. Okay, word is common in this case. All right, so let's quote that. All right, if two edges do not share a common vertex, they are not adjacent. Okay, and that is for sure. All right, so like I just said, I just showed you that AB is adjacent to BC. And so obviously, if you look closely here, they share point B or vertex B. All right, that's the common vertex here. All right, so I'm going to say yes. All right, they share a common vertex, which is B. They share a common vertex, okay, at B. Now over here, CE and BD. CE, let's go different colors here. Here's CE and BD. BD is over here. All right, they intersect, but they don't share a common vertex. So here the answer is no. There's no common vertex. All right, so we go through a bunch of examples here to get you to understand the idea of the definition. All right, because if you understand it, then you can apply it. If you can't understand it, well, then you can't apply it, nor can you understand any of Euler's theorem. So the whole idea in the beginning is to get the vocab down so you understand the vocabulary of the theorems later on, which contain all the big ideas. All right. Now, the degree of a vertex is the number of edges at that vertex. We've talked about that before. DEG is our abbreviation for degree. We understand that every loop, all right, counts twice towards the degree, and I see a loop over here. So that has degree 2 on the loop, but 2 more over here, so a total of 4 at E. We'll talk about that in a minute here. Odd vertices are ones of odd degree, and I'm talking about numbers or degrees like 1, 3, 5, 7, and so on. Even vertices have even degree, such as 2, 4, 6, 8, and so on. All right, and one of the important things in graph theory is the looking at the degrees of every vertex in the graph, so you can infer a lot of things from it, as we're going to find out. So in this case right here, I ask you to find the degree and label everything in red. So here degree A is degree 1, here is 3, 1, 2, 3, here is 1, 2, here it's 2, and here is 1, 2, 3, 4, because the loop has degree 2, plus 2 more edges, so degree 4. So these numbers that you see in red here symbolize the degree of the vertex at every point in the graph. Okay. Now the notion of a path versus a circuit is also important in graph theory. A lot of our goals and many of the problems are either to find a path or a circuit in the graph, because it has a lot of applications in real life. So what in the world is a path? And then secondly, what in the world is a circuit? So let's first of all understand one thing, that these are different phenomenons, okay? So first of all, they're different. But what is the difference? Okay, so let's go through it. A path in general is a sequence of adjacent vertices from a starting to end point. Each edge can only be traveled once. Key concept there. Just like the unicursal drawings that we did in a previous lesson here, these paths, or all paths in circuits, each edge can only be traveled once. So remember that. The length of the path is the number of edges, okay, in the path. So the key word in this one right here is number of edges. So let me just show you what I'm talking about. Let's find some paths from A to E. So one path from A to E is A to B to C to E. Okay, now it doesn't cover every edge nor every vertex, so I'm not talking about a unicursal drawing here, okay, or an Euler path or an Euler circuit or anything like that. I'm just talking about a simple path from A to E. So I don't care about how many vertices or edges it covers. Okay, so I can say that A, B, C, back to E, all right, is a path where there's 1, 2, 3 edges. One edge from A to B, then from B to C, and then from C to E. So in this case, right here, the length is 3. Now you don't have to take that path from A to E. You could go A to C, excuse me, switch that to D and then to E. That's another path. So you could go A to B to D now to E. Still has the length 3, 1, 2, 3, okay? So it has the same length, but it's a different way to get from A to E. So a path starts at one location and ends in another. A circuit is different. A circuit starts and ends at the same location. All right, it starts and ends at the same vertex. So for a circuit to exist, you got to find a path from one point back to itself. So if we wanted to find a circuit for C, what we're going to do is start at C and end at C. So start at C and end at C. Okay, so for example, there's many circuits for C here. You can go C to B to D, E, back to C. So let me repeat that. So C to B, all the way to D, to E, and then back to C. All right, so C, B, D, E, and then back to C. 1, 2, 3, 4, length 4. You can even see it in the order in here. From C to B is 1, from B to D is 2, from D to E is 3, and from E to C is 4. So this is length 4. Okay, now notice something here. We start at C and end at C. That's what I was talking about right here. That's a circuit. And that's different than a path. A path starts somewhere and ends somewhere else. A circuit has to come back to the same vertex. And there may be more than one circuit for every point. So let's talk about another one. Let's say instead of going from C to B, I could go from C to E to D to B back to C. So C to D now. All right, E. Let me see. C to, no, I can't go from C to D. That's wrong. I'm sorry. So from C to E to D. So E to D. All right, to B back to C. All right, and that has still a length of 4. So you can get from C back to C in multiple different ways. But if you get back to the same point that you started with, and that's the whole idea of a circuit, all right, you call that a circuit. It's a path which starts and ends at the same place. Now, a circuit for for E here, well, the simplest one is just E back to itself. So the simplest one is EE, which is the loop, length 1. Okay, a more fancy one, you can go from E to C to B to D back to E. So what did I just say? I said E to D to B to C back to E. And notice that we start and end at the same place. You can even loop around E if you want. You can get a little crazy here. You can start at E, and then you can go, well, you can go around the loop if you want. So EE, and then to D, and then to B, and then to C, then back to E. So you can use the loop if you want. You can do whatever you want. You get a little crazy, get a little creative. All right, so now it's time for you to practice too. So hopefully you'll be willing to turn off the video here, not turn off, just pause the video here, give the 1 through 5 a shot, and then whenever you're ready, go ahead and press play, and then we'll talk about the rest. All right, I'll give you a few minutes here. All right, we're back now, and hopefully you gave all these a shot. So one path from B to K through W, but not through S, is the following here. So let me get a highlighter here so we can start at B. Here's B. And we got to get to K, all right, B to K. But we got to go through W. So we're going to zoom all the way over here to H, to J, back down to W. You got to go through W, all right, to S, down to K. So it's kind of hard to see, right? So what you do is this. You can simplify it by this. Go B to H, up here to J, and then to W, and then up here to S, and then back down to K. So let's go ahead and, whoa. No, wait, that's not good. That's not a good example because guess what? It says, but not through S. All right, so that's an example of what not to do. One must read directions. Okay, so we got to go through W, but not through S. So let's try a different one. Okay, so we're going to start here. We're going to go to H. All right, we're going to go to J. We got to go to J. All right, now we got to go to W here, but oh, we can't go through S. So we're going to go, we're going to go right to K. All right, so B to H, zoom right across to J. All right, from J to W. All right, but not through S. All right, so don't go there, go straight to K. All right, and that has 1, 2, 3, 4, length 4. All right, so what you can do is kind of just play with it, use arrows to direct yourself and help you understand things better, use highlighters, whatever it takes. All right, on this one here, you want to find a path from H to J with length 4. Okay, so H to J. So here we go. So H to J. Okay, let's go from H to K. That's 1, 2, 3, 4. From H to J, length 4. 1, 2, 3, 4. So there we go. That's one possibility. So H to K to S to W to J. And okay, again, length 4. Is that the only way you can do it? No. You could probably do something else here, but you got to start at H. So let me erase this and we'll try a different path. So let me see. So H to K. Oh, how about W? I want to end at J. So how about to S, then to J? So count them. 1, 2, 3, 4. Length 4. So then you write it H, K, W, S, and then to J. All right? Length 4. So 1, 2, 3, 4. So it helps you sometimes to use a little bit of color in your drawings, right? So you can keep track of it, so you can see it better. All right? And count better too. All right, number 3, find a circuit of length 5. Okay, so remember the word circuit. This right here, this tells me that I got to start and end at the same place. So start and end at the same vertex. I'm just saying that because that's what the whole idea of a circuit is. Okay, many different possibilities here. So if I start at W, for example, length 5. Okay, so I start at W, I got to end at W. So let's go W, S to K, to H, over there to J, and then back to W. Let's count. So I went here. That's 1, 2, 3, 4, back 5. Okay, that's length 5. So we write it W to S to K to H to J, and then back to W. So notice that's length 5. 1, 2, 3, 4, 5. And notice also that I start at W and end at W. That's the whole idea of a circuit, guys. All right, and there's many different possibilities. You don't have to start at W. You could start at H, for example. Okay, so let me switch colors here. So if you start at H, let's go right here. Right here, so H. No, let's put it right here. I'll put OR, so H. Length 5. So you got to start at H and end at H. So H, J, and then maybe to W here, to S, to K, back to H. So 1, 2, 3, 4, and 5. All right, so H to J, down to W, to S, to K, back to W. Notice that I started, well, not to W, to H. I'm at H. Okay, so I start and end at H. That's the whole idea of a circuit. And so there's many possible answers here, and you need to realize that. Okay, find a circuit of length 1. Well, that's easy to find. You look at a loop. All right, so you got a loop right here, and BB is a loop. All right, and is length 1. And then it says find the degrees of each vertex in red. Okay, I already used red, but oh well. Okay, I'll just put the numbers at each one. So 1, 2, 3. H is degree 3. K, 1, 2, 3, degree 3. W, 1, 2, 3, degree 3. B is 2 plus 1 or 3, so degree 3 right here. J is 1, 2, 3, degree 3. S is 1, 2, 3, degree 3. So if you want to look at the, I'll put the degrees in green here, like this, so you can see them. Okay, there we go. So you can easily see them there. All right, so what in the rule is the idea of connected versus disconnected? Because this is an important concept too, believe it or not. Okay, so what we do is we say that a graph is connected if any two vertices are joined by a path. Okay, so if any, all right, two vertices are joined by a path. We say that they're connected in that case. This means, right here, that there is always, that it is always possible to travel from one vertex to another vertex in the graph. Because if there was no edge connecting them, then it would be disconnected, guys. It would be isolated, or at least part of the graph would be isolated. A disconnected graph is made up of small connected portions or parts called components. Okay? So a disconnected graph is made up of small connected portions called components. All right, so let's take a look at an example of what it means to be connected versus disconnected. So connected versus disconnected. Let's take a look at that. All right, so in the graph on the left, number 1 here, it's made up of 5 vertices, A, B, C, D, E, and F. Oh, 6 vertices, excuse me. Ooh, supposed to be an F in there. Okay, there we go. Now there is. All right, and notice that there's no vertex isolated. All right, every vertex is connected to something else. All right, therefore it's connected. If you have two pieces or two components, like on graph number 2 here, the first component, it comprises of P, R, X, and Y, and the second component, it comprises of S, T, U, V, and W. You have what is called a disconnected graph because there's no edge between R and S, and there's no edge between X and W. All right, so these are disconnected because no edge RS does not exist and XW does not exist. All right, so disconnected means that there is a missing edge. So RS, all right, and the other one down below here, XW and XW, does not exist. All right, therefore these are two different components, but put together they form one graph. Now, another major term in graph theory is what it means to be a bridge. All right, now a bridge, which is going to come into play in some of our algorithms later on, is simply an edge in a connected graph whose removal makes it disconnected. So let me say that again. A bridge, excuse me, is an edge, all right, in a connected graph. So like the one on the left in graph number 1. All right, whose removal makes it disconnected. Okay, so the key word is removal. If you remove an edge and then you have a separate component of the graph, well, then it becomes a bridge. So basically, if the only path between two vertices is one edge, then it is a bridge. Or you can think of it as a different way. If no alternative routes exist to travel between two vertices besides that edge, then it is a bridge. So let's take a look at the two graphs here and let's figure out what it means to be a bridge, because you have to identify them because it's part of our algorithm later on in some of our methods. So in graph number 1, what are the possible edges? Well, one example would be BE here. If I took this away and I erased it, boom, it's gone. So I can't erase it, but let's suppose I did. Then we'd have this triangle looking portion of the graph and this other part that looks like CE and ED connected. All right, that's if I took out this edge here. So if I took out BE and if this was gone, then I would have two separate components of the graph. So BE is a bridge. Also, if I took out this edge right here, CE, then C would be isolated. So CE becomes a bridge. Likewise, if I took out ED or DE, well then D would be isolated and we have two separate components. All right, so ED becomes another good example of a bridge. On the graph on the right, in the second graph, what would be the edges that would be classified as bridges? All right. Well, if I took out, let's say, PY, well, then P would still be connected to X and Y would still be connected to R. So PY is not a bridge. If I took out PX, P would still be connected to Y and X would still be connected to R. So that's not a bridge either. If I took out ST, this one up here, S would still be connected to W and T would be connected to W and V. So ST is not a bridge. If I took out SW, S would be connected to T and W would be connected to T. So that's not a bridge. If I took out TW, then I'd have two separate components. In fact, I'd have three total. I'd have one, and then two, and then three. So TV is a bridge. Likewise, if I took out UV, then U would be isolated. So UV would also be a bridge. So it's really important, and you don't know this because you haven't seen Euler's theorems yet, to identify, the bridges, whether in a connected or disconnected graph. It's really important to understand the idea of a circuit versus a path, and also the degrees of a graph, so you can understand Euler's theorems coming up. So let's do this. Turn on the next page and let's practice. Okay, I want you to draw the graph that gives this, given the certain properties up here. And if you would like, you can pause the video and go for it, and then press play when you're ready, or you can keep it going. It's totally up to you. It depends on your need, all right, and how much experience you have. So if you need to listen to it, then you just let it run. If you want to pause and go for it, you can pause the video and then play it in a couple minutes after you tried them all. All right, so make a decision right now. Either pause the video or let it run. All right, so let's go through some practice here of drawing some graphs to satisfy the given properties. So here I need 6 vertices. All right, you can line them up in any fashion you want. You need 6 edges. So 1, 2, 3, 4, 5, 6. So that's one possibility. Or let's draw another one. Let me put it in blue. So 6 edges. 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, that's 7, so that's not good. That's too many. Let me redraw this. Put too many in there. 1, 2, 3, 4, 5, 6. We only want 7. 1, 2, 3, 4, 5, 6. Oh, there we go. 1, 2, 3, 5, 6. There we go. So 6 edges, 6 vertices. Get creative. You can draw all kinds of graphs. You just have to learn how to satisfy the given conditions. Like this is a new one. We haven't done this one yet because I want 2 bridges in this one. So 6 vertices. 1, 2, 3, 4, 5, 6. Okay. All right. And 2 bridges. And now it can have as many edges as you want because it doesn't say. So let's put in a couple of some vertices here, but I need a bridge. So how about right there? So this becomes a bridge because let me put some letters in here so I can talk about it. So BC is a bridge because if you eliminate edge BC, then C is isolated. If I put segment EF in here, this also becomes a bridge. Let me put them in red. Bridges in red right here. There are 2 bridges in red, BC and EF, because if you eliminate them, C and F would be isolated and may have separate components. All right, and let's continue here. So we got these 4 vertices here. We'll call them A, B, C, and D. Let's go plot them, label them, and start drawing, man. Just go crazy here. So AB, AC, AD, all right, and BD. Woohoo, that was tough. All right, so you got a vertex and an edge set. What would be the bridge on that? It doesn't ask you that, but what would be a bridge? Would it be AB, BD, AD, or AC? Which one, if you eliminate it, would make something another component of the graph and make it disconnected? I think it would be right here. This would be a bridge. because C would be isolated and you would have a separate component. Okay, on this one here, let's go P, Q, R, S, and T. You just plot the points and you start drawing. Go crazy, like I said. So PQ, let's draw some segments here, some edges. So I'm just reading here. PQ, QR, RR. Ooh, that's a loop. Okay, whoosh, loop right there. All right, RS. Put in the sound effects. It makes it more fun. So RS. All right, ST. All right, and TP. Right up there. Okay, there you go. That's all there is to it. All right. Okay, next one, a little more challenging. Three even vertices. Four odds. One, two, three, four. Okay, so you got 7 points here. So you want three even vertices. So let's get some edge makers here. So let's see, let's put some in. Okay, man, let's see. So now I have that's degree 1. I'm just playing with this here. That's degree 3, that's odd. Now I have 2 odds. I want 4 odds. So I've got, let me see, degree 1, degree 3, degree 3. Let me see if I connect here. That's not going to work. Let's see here. Degree 3, degree 3, degree 2, degree 2. Let me see what would happen here. 1, 2, 3, 4. That's degree 4. Degree 1. So degree 1, degree 4, degree 3, degree 3, degree 1, degree 2, degree 2. So we've got 1, 2, 3 evens, 1, 2, 3, 4 odds. Ooh, we did it. All right, 3 evens. We want 3 even vertices, 1, 2, 3, and then 4 odd vertices. Okay, so you just get creative here and create a graph given the information here. That's all you do. And experiment. It's not that hard. You just got to go for it. 5 vertices with 8 edges, and you want to show it's connected. So 1, 2, 3. Oh, let me spread these out a little bit. So 1, 2, 1, 2, 3. You want 8 edges, and you want it connected. So here we go. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. Oh, okay. 8. There you go. And it's connected. So there's an example of something with 5 vertices and 8 edges. Okay. How about disconnected? All right. So 1, 2, 3, 4, 5, 8 edges. Okay, here we go. 8 edges. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And it's disconnected. I did it. Okay, 8 edges, disconnected. There we go, guys. That's all there is to it. So just play with it, have a little bit of fun, and make sure, guess what? You do your homework, all right? So give it your best, and make sure you do your homework right now. So let's take out your homework sheets. What do they look like? Well, I'll show you. I'll show you what they look like because I handed them out before. So let me see. Let me see. What does it look like? So chapter 5, homework pages, book pages. Here we go. All right. So take out your notes on this is copied from the book. So your book pages right here. All right. Get your spiral out, guys, and you're going to be doing 1, 4, 6, and 8. So you already did actually 1. So scratch 1. Just start at 4, okay? Because you did 3, 5, 7, and 9. All right. Now's the time to do 4. All right. 6, 8, 10, so on. So let's get your homework set up here. Those are the solutions. You know what? Let me just add another page here. So we're going to clip in. We're going to talk about how to do number 4. You don't need to watch me do this, guys. Okay, I'm just getting ready for a discussion here. So do number 4, 6, 8, 10. All right, 11, 13. And I'll see you in my next lesson. This is Mr. Ains. We're signing off. Ciao, guys.